There's a serious electrical safety concern arising from inadequate bonding and improper neutral switching at multiple cell sites. The use of 3-wire generator connections and manual transfer switches that don't switch the neutral pose significant risks. These risks include potential electrocution and equipment damage. Failing to properly bond the neutral and switch it and transfer switches violates the National Electrical Code, or NEC. The NEC mandates bonding of the neutral and switching of all current-carrying conductors to ensure proper operation and safety. Presented are two undesirable options. Firstly, maintaining the neutral bond in generators, which offers some bonding between neutral and ground but doesn't address the lack of neutral switching in transfer switches, resulting in ongoing safety hazards. And secondly, disconnecting the neutral bond in generators and ignoring violations, which removes the neutral bonding but does not fix the basic problem of incorrect neutral switching, which raises the possibility of electrocution and equipment damage. Neither option is acceptable from an electrical safety standpoint. Several steps should be implemented. Firstly, engage legal counsel. Seek legal guidance to clarify liability issues and determine the most appropriate course of action. Secondly, document the hazards. Thoroughly document the electrical risks related to the current setup and the possible repercussions of inaction. Thirdly, escalate the issue. Bring the matter to the attention of higher management or regulatory bodies to emphasize the seriousness of the situation. Fourthly, insist on compliant installations. Demand that all cell sites comply with electrical codes. This involves replacing 3-wire connections with 4-wire connections and installing manual transfer switches that switch all current-carrying conductors, including the neutral. Fifthly, protect yourself. Refuse to take any actions that could increase liability or jeopardize electrical safety. The contractor should not be released from liability for installing non-compliant equipment. A company's utility status does not excuse them from complying with electrical codes. The safety of employees, the public, and company assets should be of utmost importance. The neutral is a critical conductor in electrical systems, and its proper handling is essential for safety and performance. The neutral's primary function is to provide a return path for current in a single-phase or 3-phase electrical system. In a properly functioning system, the neutral conductor carries the imbalance of current between the phases, ideally carrying little to no current in a balanced 3-phase system. The neutral is typically grounded at the service entrance to provide a reference point for voltage and to facilitate the clearing of ground faults. Grounding the neutral creates a low impedance path for fault currents to return to the source, tripping circuit breakers or blowing fuses to de-energize the circuit. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding of electrical systems to ensure safety. Article 250 of the NEC covers grounding and bonding requirements, including the size of grounding conductors, the methods of grounding, and the requirements for bonding metal enclosures and equipment. The NEC requires that the neutral conductor be grounded at the service entrance and at the source of separately derived systems such as generators or transformers. The grounding electrode system typically consists of a grounding electrode conductor connected to a grounding electrode, such as a ground rod, a metal water pipe, or a concrete encased electrode. Bonding is the process of connecting all non-current carrying metal parts of an electrical system to create a low impedance path for fault currents. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. The NEC requires bonding of metal enclosures, raceways, equipment, and other metal parts that are likely to become energized. Bonding is typically accomplished by using bonding jumpers or bonding conductors to connect the metal parts together. Improper grounding and bonding can create dangerous conditions, such as voltage differences between metal parts, which can lead to electric shock. Ground faults can also create excessive current flow through unintended paths, leading to overheating and fire hazards. It is crucial to follow the NEC requirements for grounding and bonding to ensure the safety of electrical systems. Transfer switches are used to switch between different power sources, such as utility power and generator power. Transfer switches can be manual or automatic, depending on the application. Manual transfer switches require manual operation to switch between power sources, while automatic transfer switches automatically switch to the backup power source when utility power is lost. Transfer switches must be properly sized and rated for the intended application. The transfer switch must be able to handle the maximum current and voltage of the electrical system. Transfer switches must also be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or UL. There are two main types of transfer switches: firstly, break-before-make transfer switches, and secondly, make-before-break transfer switches. Break-before-make transfer switches disconnect the load from one power source before connecting it to the other power source. This type of transfer switch prevents the two power sources from being connected at the same time, which can damage equipment. Make-before-break transfer switches connect the load to the second power source before disconnecting it from the first power source. This type of transfer switch provides a seamless transfer of power, but it can also create a momentary parallel connection between the two power sources, which can cause problems if the power sources are not synchronized. The NEC requires that transfer switches be installed in accordance with the manufacturer's instructions. Transfer switches must be accessible for inspection and maintenance. Transfer switches must also be properly labeled to indicate the power sources and the operating position of the switch. The neutral conductor must be switched in a transfer switch to prevent circulating currents and voltage imbalances. When the neutral conductor is not switched, current can flow through the grounding system, creating a voltage difference between the neutral and ground. This voltage difference can cause equipment malfunction and increase the risk of electric shock. The NEC requires that the neutral conductor be switched in a transfer switch for separately derived systems such as generators or transformers. The NEC also requires that the neutral conductor be switched in a transfer switch when the grounded conductor is used for grounding equipment. Ground fault circuit interrupters, or GFCIs, are used to protect people from electric shock. GFCIs monitor the current flowing in the circuit and detect any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI trips the circuit, interrupting the flow of current. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. The NEC requires that GFCIs be installed in all 120 volts, 15 amps and 20 amps receptacles and dwelling units that are located in bathrooms, garages, and outdoor areas. GFCIs are also required for receptacles located within 6 feet of a sink or wet bar. GFCIs must be tested regularly to ensure that they are functioning properly. The NEC recommends that GFCIs be tested monthly by pressing the test button on the device. Arc fault circuit interrupters, or FSIs, are used to protect against fires caused by arcing faults. Arcing faults occur when electricity jumps between two conductors, creating a high-temperature arc that can ignite nearby materials. FSIs detect arcing faults by monitoring the current flow in the circuit and detecting abnormal patterns that are characteristic of arcing. When an arcing fault is detected, the FSI trips the circuit, interrupting the flow of current. FSIs are required in many locations, such as bedrooms and living rooms. The NEC requires that FSIs be installed in all 120 volts, 15 amps and 20 amps branch circuits that supply dwelling unit bedrooms, living rooms, and other areas where arcing faults are likely to occur. FSIs must be tested regularly to ensure that they are functioning properly. The NEC recommends that FSIs be tested monthly by pressing the test button on the device. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges are transient over-voltage events that can damage or destroy electronic equipment. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the excess voltage to ground, protecting the equipment from damage. SPD are available in a variety of types and sizes, depending on the application. The NEC recommends that SPD be installed at the service entrance and at sensitive electronic equipment. SPD must be properly rated for the voltage and current of the electrical system. SPD must also be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or UL. Electrical safety is paramount in all electrical work. Always follow safe work practices and wear appropriate personal protective equipment, or PPE. De-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized. Lockout and tag-out procedures must be followed to prevent accidental energization of the circuit. Never work on electrical equipment in wet or damp conditions. Use insulated tools and equipment. Avoid contact with energized parts. Report any electrical hazards to your supervisor or employer. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical installations. The NEC is updated every 3 years to reflect changes in technology and safety practices. The NEC is adopted by many states and local jurisdictions as the basis for their electrical codes. The NEC covers a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. It is important to be familiar with the NEC requirements for electrical work. The National Fire Protection Association, or NFPA, is a non-profit organization that develops and publishes codes and standards related to fire and electrical safety. The NFPA publishes the National Electrical Code, or NEC, as well as other codes and standards related to fire protection and life safety. The NFPA provides training and education programs on fire and electrical safety. The NFPA also conducts research on fire and electrical hazards. Occupational Safety and Health Administration, or OSHA, is a federal agency that is responsible for ensuring the safety and health of workers in the United States. OSHA sets and enforces standards for workplace safety and health. OSHA conducts inspections of workplaces to ensure compliance with its standards. OSHA provides training and education programs on workplace safety and health. OSHA also investigates workplace accidents and injuries. The use of generators in cell site applications requires careful consideration of several factors. Firstly, generator sizing. The generator must be sized appropriately to handle the load requirements of the cell site. The load requirements include the power needed for the cell site equipment, such as radios, servers, and lighting. The generator must be able to provide sufficient power to start and operate all of the equipment simultaneously. Secondly, fuel supply. The generator must have a reliable fuel supply to ensure continuous operation during a power outage. The fuel supply can be diesel, natural gas, or propane. Fuel supply must be sized appropriately to provide enough fuel for the expected duration of the power outage. Thirdly, ventilation. The generator must be properly ventilated to prevent overheating. The generator produces heat during operation, and if it is not properly ventilated, it can overheat and shut down. The generator must be located in a well-ventilated area, or it must be equipped with a ventilation system. Fourthly, maintenance. The generator must be regularly maintained to ensure reliable operation. The maintenance schedule should include regular inspections, oil changes, and filter replacements. The generator should also be tested periodically to verify that it is functioning properly. Fifthly, transfer switch. A transfer switch is required to switch between utility power and generator power. The transfer switch must be properly sized and rated for the intended application. The transfer switch must also be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or ALL. Finally, grounding. The generator must be properly grounded to prevent electric shock. The grounding system must comply with the requirements of the National Electrical Code, or NEC. The generator must be connected to a grounding electrode system, such as a ground rod or a metal water pipe. The grounding conductor must be sized appropriately for the generator's output current. 3-wire generator connections are not recommended for cell site applications. 3-wire generator connections do not provide a separate neutral conductor. This can create voltage imbalances and increase the risk of electric shock. 4-wire generator connections are recommended for cell site applications. 4-wire generator connections provide a separate neutral conductor. This helps to balance the voltage and reduce the risk of electric shock. The neutral conductor must be switched in the transfer switch to prevent circulating currents and voltage imbalances. When the neutral conductor is not switched, current can flow through the grounding system, creating a voltage difference between the neutral and ground. This voltage difference can cause equipment malfunction and increase the risk of electric shock. The NEC requires that the neutral conductor be switched in a transfer switch for separately derived systems, such as generators or transformers. The NEC also requires that the neutral conductor be switched in a transfer switch when the grounded conductor is used for grounding equipment. Manual transfer switches are not recommended for cell site applications. Manual transfer switches require manual operation to switch between power sources. This can be time-consuming and unreliable. Automatic transfer switches are recommended for cell site applications. Automatic transfer switches automatically switch to the backup power source when utility power is lost. This provides a seamless transfer of power and ensures continuous operation of the cell site equipment. The non-switched neutral in the manual transfer switch is a serious safety hazard. The non-switched neutral can create voltage imbalances and increase the risk of electric shock. The non-switched neutral can also cause equipment malfunction. The non-switched neutral violates the requirements of the National Electrical Code, or NEC. The NEC requires that the neutral conductor be switched in a transfer switch for separately derived systems such as generators or transformers. The NEC also requires that the neutral conductor be switched in a transfer switch when the grounded conductor is used for grounding equipment. It is recommended to replace the manual transfer switches with automatic transfer switches that switch the neutral conductor. It is also recommended to replace the 3-wire generator connections with 4-wire generator connections. These changes will improve the safety and reliability of the cell site electrical system. Consulting with a qualified electrical engineer or contractor is important. Electrical work can be dangerous, and it is important to hire a qualified professional to perform the work. A qualified electrical engineer or contractor can assess the electrical system and make recommendations for improvements. A qualified electrical engineer or contractor can also ensure that the electrical work complies with the requirements of the National Electrical Code, or NEC. Always prioritize electrical safety in all electrical work. Follow safe work practices and wear appropriate personal protective equipment, or PPE. De-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized. Lockout and tagout procedures must be followed to prevent accidental energization of the circuit. Never work on electrical equipment in wet or damp conditions. Use insulated tools and equipment. Avoid contact with energized parts. Report any electrical hazards to your supervisor or employer.